Hello! Today's topic is graphing trig functions with more transformations.
All right, so the first one I'm going to sketch for you, the first example, let's keep it reasonably simple to start with. Let's have a look at the graph of y is equal to 2 cos x minus 1 over the domain of 0 to 4 pi. This is something that could quite easily get asked of you. Can we sketch that function? First of all, I go through the usual process of what's the shape? Well, we know the shape is a cos graph, so it's going to sort of look like that. What's our period? Period is equal to 2 pi over n, which is equal to, in this case, 2 pi, because our n value is 1. What's our amplitude? Our amplitude is equal to 2, since that's our a value in this case. And already I could start drawing some axes. I'm going to go to 4 pi. So I need a line roughly halfway at 2 pi, a line roughly there at pi and at 3 pi. And then we can divide those up as well. So that one there was 2 pi, pi, 3 pi, 4 pi. That's enough of an axis at the moment. Our maximum, straight away, what's our amplitude? Well, it's 2. So what's our minimum and maximum? One question you're going to get asked a lot is, just from looking at a function like that, can you tell what the minimum and the maximum values are? We're going to do it a lot more when we're doing application problems as well. But it's good right now to think straight away what's our minimum and our maximum. And always, essentially, we can think of it as, well, since we're starting at 0, our a value is going to go up and down that much. So that would make our maximum value 2 and negative 2. And then after we do that multiplication, we then do this translation as well. So we're going to subtract 1 from both of those values, which is going to give me a maximum of 1 and a minimum of negative 3. Hopefully people can see where that comes from. We know that cos itself goes between 0 and 1. Goes between negative 1 and 1. We're multiplying that by 2, so that means it's going between negative 2 and 2. And then we're subtracting 1 from both those values, so it's going between negative 3 and 1. So I'm going to put some dotted lines in this graph to show that. That's my value at 1. Might extend that just to try and get the scale a little bit better. We're going to extend that at negative 3. Now, this cos graph doesn't have any reflections and it doesn't have any horizontal translations. There's nothing inside the brackets there. So no dilation, no horizontal dilations, no horizontal reflections. We can tell straight away we're going to start there and go downwards, but I'm not actually going to draw anything yet before I determine my x and y intercepts. So the y-intercept, we can calculate the usual way. Y-intercept occurs when x equals 0, and thus y is equal to 2 cos 0 minus 1. Cos of 0, we can draw that if you need to, but cos of 0 is going to be our horizontal value which goes across, which is 1. So 2 times 1 minus 1, which is equal to 1. Now, we're up to our x-intercepts. I should also point out, thus, we're going to get, maybe before I jump to x-intercepts, we can also interrupt this by saying we're going to get the maximum y value is equal to 1. That's going to occur at an x value of 0 and at the period, which is 2 pi and 4 pi. So once I work out what one maximum is, I can just add the period each time to get the other ones. And we know that our minimum values, I talked earlier, back here I talked about how we can't make the assumptions that we've got things every quarter. We don't necessarily know that that's going to be a quarter and a quarter. But what we do know still is that the maximums and the minimums must be half a period apart. So thus, if our maximum is going to be at 0 and at 2 pi, thus if we're going to get a maximum value there and there, then our minimum value has to be between those at pi. So I can also write down here minimums, again, we're going to get at x equals pi and at 3 pi. And so we can sort of tell that our graph is going to do that sort of shape. And I could pretty much sketch it in now if I wanted to get something that looks like, except I haven't got those intercepts very accurate. We could sketch that in, but a question will probably ask us to find the x-intercepts, and we can't make any assumptions about where they are. I'm actually going to undo that. I'll leave my little red dots there for maximum and minima. Let's calculate where our x-intercepts are, and then we'll sketch it in. So in this case, my x-intercepts occur at y equals 0. So 0 is equal to, go back up, look at our function. 0 is equal to 2 cos x minus 1. Thus, adding 1 to both sides, 1 is equal to 2 cos x. So a half is equal to cos of x. Now I can look up my table of exact values to work out where cos of, to work out what value of cos gives me a half. And I don't have my formula sheet in front of me, so I have to flip back earlier. Cos of a half is pi on 3. And we also know that cos is positive in that quadrant and that quadrant. So I'm going to get solutions at, sorry, one thing I should point out, I skipped the adjust the domain step because we don't have to adjust the domain where there's nothing inside our trig function brackets. If it's just x, there's no domain adjustment required. So in this case, we know that our base angle is equal to pi on 3. And thus we're going to get solutions at x equals, and I usually like to draw a line that starts at 0, goes through my domain like that. So that's 0 to 4 pi. Remember, we're sketching this over 0 to 4 pi. So I'm going to get a solution there, which is pi on 3. And at 2 pi minus pi on 3, I'm going to jump, now that we've done this a few times, we can jump straight to writing that down as 5 pi on 3. I'm hopeful that everyone knows where that came from. So 5 pi on 3. And we're also going to get one at 2 pi plus pi on 3, which is 7 pi on 3. And I'm going to get one at 4 pi minus pi on 3, which is 11 pi on 3. So there's some mental maths to jump to those fractions. I told you right at the beginning that you're going to be doing that sort of stuff a lot, and sure enough, we are. So those are my solutions, pi on 3, 5 pi on 3. Let's have a look back up here. That's pi on 2, so 5 pi on 3 is sort of there. 5 pi on 3 is almost at 2 pi, so that's going to be there. And then 7 pi on 3 is there, and 11 pi on 3 is there. And so now I just have to try and draw a curve that goes through those points. And then we like to make sure that we have labeled our endpoint. So in this case, 4 pi, comma 1. We also like to label out any, you don't have to label every maximum and minimum when there's lots of them, but you should label at least one. So in this case, I'm going to label that minimum as well, 3 pi, comma, -3. And we do like to label all our x-intercepts. Let's label that endpoint there, which is 0, 1. And my x-intercepts, as I found out down here, were pi on 3 and 5 pi on 3. I didn't put that in a very good place. 5 pi on 3 and 7 pi on 3 and 11 pi on 3. And we're done. Any questions before I move on to a more complex example? I know, that seems complex enough, and it's going to get worse. I should point out the next really complex one that I'm going to do is about as hard as it gets. This next one is definitely an A standard question. There's going to be a lot of stuff going on here. So let's have a look at let's have a look at y is equal to 2 sine 2x minus pi on 3 minus √3. There's a lot going on there, so I won't overcomplicate it with a difficult domain. Let's keep our domain over 0 to 2 pi. All right. So starting from the beginning, what's our shape? It's a sine graph, so I'm going to do that. What's our period? Period is equal to 2 pi on n, which is 2 pi on 2, so that gives us a period of pi. What's our amplitude? Our amplitude is 2. Thus, our maximum is going to be the 2 minus √3, and our minimum is going to be 2 negative 2 minus root 3. Those are both, it's good to at least label those as y values. Should have done that in the first place to say these are the y values that are the maximum and the minimum, so that later on we can, under there, put up where our x values, x maximum and minima are. All right, I like to do the y-intercept next. It's usually nice and simple. So in this case, y-intercept is y is equal to 2 sine 2 times 0 minus pi on 3 minus root 3, which is 2 sine negative 2 pi on 3 minus root 3. So now we have to work out what sine of negative 2 pi on 3 is. That's going to be down around there somewhere. So sine is going to be negative because we're in that quadrant. And our base angle is going to be pi on 3. So we can look up pi on 3 on our table of exact values and know that sine of pi on 3 is root 3 on 2. So this is 2 lots of negative root 3 on 2 minus root 3, which is equal to, that cancels out with that. We're going to get 2 lots of negative root 3, so that's negative 2 root 3. That's where our y-intercept is. Let's think about where our maximum values are as well. We know that they're going to occur at a y. What I mean by that, a quick sketch. We know that our maximum value is going to occur at 2 minus root 3, but we don't know whether it's going to be there or there or there or there or there. So let's work out our x value of where our maximum occurs. I'll just undo that because I'm going to use that space for something else. So where does our x value, what's the x value of our maximum, I should say. And so let's remember that the maximum value for sine always occurs at pi on 2. Our maximum value for sine always occurs at pi on 2, going straight upwards. So to work out where our maximum occurs, I know that pi on 2 must be equivalent to whatever's inside the bracket. So I can solve this equation here to work out where my max value is. Divide both sides by 2 gives me pi on 4 is equal to x minus pi on 3. Adding pi on 3 to both sides, well, the common denominator is 12, so that becomes 3 pi on 12, and then I'm adding 4 pi on 12, and so that turns it into 7 pi on 12 is equal to x. So that's where my maximum is. It's 7 pi on 12, and then I also know that it's going to be that plus a period each way. So I can start sketching something now. I'm going to put 2 pi there and pi there, pi on 2, 3 pi on 2. Our maximum is going to be 2 minus root 3. Root 3 is a little bit less than 2, so our maximum is not going to be very high off the line. So that's going to be 2 minus root 3. And then our minimum is going to be down here somewhere. Whoops, that one should have been a dotted line. Negative 2 minus root 3 is down there. So I'm going to get a maximum at 7 pi on 12. Think about where that is in terms of as a fraction. 7 on 12 is a little bit more than half, so that's going to be a little bit more than pi on 2. Oh, sorry, that was my maximum, not my x-intercept. So that's going to be a little bit more than pi on 2. And then we're also going to get one every period after that. So if it's 7 pi on 12, a period is pi, which is 12 pi on 12. So I'm adding 12 pi on 12 onto that. That's where my next maximum is going to be, 19 pi on 12. Or we can also think of it as, well, I know that sort of this distance here is pi. That's my period. And so I'm going to add sort of roughly the same distance there onto that. So we can visualize it that way. There's a few ways to get this in about the right place, but yes, we're going to have a maximum there and there. In this case, due to symmetry, we can take some shortcuts. Our maximum is a little bit past there and a little bit past there. So our minimum is going to be a little bit past there because it has to be halfway in between. So I'm just going to put a minimum point down there. There's a bit of let's show it algebraically, just because we like to make sure of these things. And how I can show it algebraically is obviously that we've got two maximums. We've got this one here, 7 pi on 12, and this one here, 19 pi on 12. We know that our minimum has to be halfway between them. What's halfway between 7 and 19? 7 plus 19 is 26, divided by 2 is 13 pi on 12, which sure enough is the same little distance. This is all of these are sort of pi on 6 more than, sorry, not pi on 6, pi on 12 more than our halfway marks. So 6 pi on 12 is halfway, but we're 1 pi on 12 more than that. And 18 pi on 12 is our halfway, but we're 1 pi on 12 more than that. So I'm using a lot of symmetry tricks here, knowing that the pattern is repeating, know that what you do in one place occurs in the other. So we've pretty much done everything apart from finding and labeling our x-intercepts. And so let's do that now. Oh, let's also do one more thing. Let's remember, we know that we're going to be starting, we're going to be starting down here. We've already worked out that our y-intercept was -2 root 3. I don't know quite where that is or how big it is, but it's got to be less than -2 minus root 3, so it's somewhere there. The question also becomes, do we go down or do we go up? And we can sort of work it out from our diagram if you've done a reasonably good one, that if there's a period, if this is going from -0.5 up to there, and it's kind of come down in the same period, it's going to get back to there. So we've actually missed, we should be able to recognize that when I was doing my maximum and my minima, we've actually missed one as well, because if the difference between the maximum and the minimum is 6 pi on 12, then that means subtracting 6 from 7 pi is also going to give us a minimum at pi on 12, or at 1 pi on 12. So we're going to get a minimum there, just following this pattern. That's a period away. So this one here is also a period away from that one there. Thus, our graph needs to go down before it goes up. So I can almost sketch it in now. Oops, as I said, it's a bit wobbly. It's very hard on an iPad. And where we finish is going to be where we start and also going in the same direction, assuming that our period is some sort of factor of our domain. In this case, we're going over 0 to 2 pi, and our period is exactly pi. So since our period is an integer, is a multiple of our period, we know that we're going to finish wherever we start. So I can label this point here as 0, -2 root 3. I can label this point here as 2 pi, -2 root 3. And now the only thing left that I need to worry about are my x-intercepts. I say it like it's only minor, but they are painful because we have to solve this equation. So 0 is equal to, I can't get that both on the screen, I'm going to have to remember it, oh dear. 0 is equal to 2 sine 2 lots of x minus pi on 3, was it? Black. Minus root 3. Solving this equation, root 3 over 2 is equal to sine 2 lots of x minus pi on, whoops, that's the wrong symbol, pi on 3. All right, I need to adjust my domain. It was 0 to 2 pi, but now I have to plug my 0 and my x value in there. So that's the domain of x, which means, sorry, I'd like to write this in a different way. I just ran out of space. I'll do it properly. X is an element of 0 to 2 pi, which means that 2 lots of x minus pi on 3 is an element of, I'm going to work out what I get when I plug in 0 and 2 pi. So plugging in 0, not that one, plugging 0 into x gives me -pi on 3 times 2, which is -2 pi on 3. And plugging 2 pi into x gives me 6 pi on 3. Subtract 1 gives me 5 pi on 3. And then we're multiplying that by 2, which gives me 10 pi on 3. Now, what's my base? Where am I going to get solutions? Sign is positive, so I'm going to get solutions there and there. And for my domain, I'm going to start at -2 pi on 3, which is down here, and go around to 10 pi on 3, which is a little bit more than 3 pi. So sorry. So I'm going to start here, which is negative 2 pi on 3. I'm at 0. I'm at pi. I'm at 2 pi. I'm at 3 pi. And then a little bit further puts me there. So I'm going to get solutions there and there and there and there. So looking up our table of exact values, we're trying to solve where sine of something gives us an answer of root 3 on 2. And the something obviously needs to be a base angle of pi on 3. So if our base angle is pi on 3, we're going to get a solution. Remember that nothing's up until there. That's our first solution, which is going to be at pi on 3. And what is equal to pi on 3? The answer is this thing that we had here inside our trig function. So that gives me 2 lots of x minus pi on 3 is equal to pi on 3. Continuing around, we get another solution there, which is going to be at pi minus pi on 3. So that's 2 pi on 3. And continuing around, we get one there, which is 2 pi plus pi on 3. That's 7 pi on 3. And continuing around, we get one there, which is at 3 pi minus pi on 3. That's 8 pi on 3. Now we need to get rid of that 2 coefficient at the front. So I'm going to divide everything by 2. If I divide everything by 2, I get pi on 6. So I'm just doubling each denominator. 2 pi on 6, 7 pi on 6, and 8 pi on 6. Now I need to add x on 3. Sorry, that shouldn't be an x, that should be a pi. Whoops. Now I need to add pi on 3 to each of those values. Pi on 3 is the same as 2 pi on 6, so I really just have to add 2 to each coefficient. So my x values are going to be 3 pi on 6 and 5 pi on 6 and 9 pi on 6 and 10 pi on 6. And thus, simplifying each of these gives me pi on 2, 5 pi on 6, 3 pi on 2, and 5 pi on 3. Right, let's go back up. We'll label those on the graph. What we'll notice is that this, I just calculated that I was going to have an x-intercept at pi on 2, but clearly my graph doesn't go through there. This is one of the reasons why we usually don't draw our graph until we've got all the information. I made a mistake to draw it early, partly because I just wanted to show you my brain process earlier. So let's have another think about it. I've got the ability on the iPad to just rub it out. You will have to be more careful in a test or an exam, so I suggest doing all your calculations before you actually get to sketching the graph. All right, so what do we know? Well, we've got our maximum points and our minimum points worked out, although we might have to adjust those as well, because if we've got an x-intercept at pi on 2 and another x-intercept at 5 pi on 6, which is nearly pi, then our maximum should actually be halfway between those. So I didn't get my scale very good to start with, but it makes a lot more sense if you just draw these points in after you've calculated everything else. The next one was at 3 pi on 2 and also at pi on 12, at 5 pi on 3. And I should probably erase my minimums and put those halfway between where my x-intercepts are as well. So that looks like it's about there. This one's about there. That's good enough. Let's now sketch our graph. Again, I'll point out this is hard on an iPad to get the curve smooth, but I'll do my best. And we're finished with a curve that looks like that. I've still got my endpoints labeled from when I did it last time, but I should label my x-intercepts. Now, pi on 2 is already labeled, so let's label this one with my 5 pi on 6. And this one was 3 pi on 2, but I need to label this one as my 5 pi on 3. And in the process of moving my maximum, we'd like to have our maximum, at least a maximum and a minimum labeled as well. So this maximum here, let's remember I worked this one out to be that value there, 19 pi on 12, comma, the maximum value is 2 minus root 3, and have a minimum value labeled as well, which is going to be 13 pi on 12, comma, negative 2 minus root 3. And I'm done. Let me preemptively answer a few of your questions. How long would that take you? Well, in a test, you probably wouldn't be given, you might be given a question that just says sketch that, but if you do, it'll be worth a lot of marks. Like, I don't know, I'm 7 or 8, but I haven't often seen that. More often they'll give you simpler questions and it won't be that involved. Or if there is a graph that's that involved, then some of the steps will have been done for you. So it might say, don't calculate the Xintercepts, or it might say, it might tell you that immediately that what the Y-intercept is, and it might tell you where the maxima and minima are, or various other things. So I don't think in a test or an exam situation you would have to do that entire thing. The first time you do one, it will probably take you 15 to 20 minutes, but you do need to get reasonably good at it just because so you know the process. And it is possible that you get a question like that, even though it's unlikely. And you should be able to get it down to being able to do those in under 10 minutes. But as I say, there's a lot going on there. I've put some questions into the sector online lesson. And so exercise 6G on page 281. Question 2A and D are reasonably simple to start with. They're both fairly similar to the first example that I did. And then you'll get to some more complex ones later on. This is as hard as sketching is going to get. You're not going to have to sketch anything more complex than this. When we get to application problems, you might sketch something. I should just mention now that where we're going to a bit later, what happens if this n value here is a multiple of pi? Quite often you might get something like, can you sketch something like 12 sine pi on 12, lots of x minus 4 or x minus 3 or something, plus 7. This is what you'll get really typically in an applications problem. And it's going to change our period because remember, normally our period is 2 pi on n, but that's 2 pi on 12, which means our pi's are going to cancel out and we're going to get a period of 24. So anything that's cycling by the daylight might give you a period like this. So for example, if we were tracking the temperature of the air over the course of a day, it might track like that because we'd have it heating up in the morning, cooling down in the afternoon and at nighttime, and it's going to get a 24-hour cycle. So if you want something that is cycling 24-hourly or 365 over a year, something, if you're dealing with a tilt of the Earth's axis, all of these things are trigonometric functions, then you're going to get a different sort of value there. That's going to make things a little bit more complex, but not that much more. And so if we practice these skills that I've talked about today, then by the time we get to application problems, which won't be until next term based on our new schedule, we were going to get to it this term if we didn't have this distance learning interruption. But now that we've done those, it's going to be next term before we finish our applications and have a test at the beginning of next term. All right, I'll stop talking